Hi everyone. In this video we're going to talk a bit about viscous friction, or how are we going to model the friction or drag on an object moving through a fluid. We're going to do really two cases. First is going to be a generalized drag equation. Second is a specific case, and this is Stokes' law. And then the third, we're going to talk about a handful of other situations in just fairly general terms. Perhaps you're doing things with bearings, perhaps you're working with hypersonic flow, etc. So let's go ahead and get started with the drag equation. Here's our generalized drag equation. We're solving for the drag force on an object, and this is equal to 1/2. First of all, this is rho, so this is your density, and this is the density of the fluid, and this is of course in units of kilograms per cubic meter. Next, CD. CD is a drag coefficient. And what the drag coefficient models, and this is actually unitless. What the drag coefficient models is the effects of things like geometric shape on the flow, and also the Reynolds number. So the Reynolds number is a unitless number characterizing the ratio of inertial forces to viscous forces. So what that means is when your object, or perhaps the flow around it, when the relative velocity between the flow and your object is very large, then the inertial effects are very large. So as the flow increases, the inertial effects increase and your Reynolds number becomes larger. At low Reynolds number, you have a very smooth flow. This is called laminar. And at very high Reynolds number, that laminar flow can begin to break down, and this is turbulence. You could also think of this as a chaotic flow. Now, between laminar and turbulence, there is going to be a little transition region, and depending on whether this is flow through a pipe or whether it is external flow over an object, in the case of an airplane or a rocket, then the actual value of this Reynolds number, which it kind of represents the boundary between laminar and turbulence, that value is going to change depending on situation. But the effects of things like geometry and Reynolds number is modeled by this drag coefficient. Next, A. A is the area, and of course this is meters squared. And when we talk about the area here, we're saying what is the area of your object that is impacting the flow. So the front-facing area of your object. And then this last one, V. Let's talk about V for just a moment. V is the relative flow, or relative, let's say relative velocity. Now, notice in this equation, if you look up this drag equation, this is how you usually see it written. You'll see it as V squared. There's a problem with that. Velocity is a vector, so you can't do V squared. So in reality, what this is V dot V. Now, if you do V dot V, you get the magnitude of the velocity squared, but you lose the vector notation. Dot product is going to yield a scalar. So if we want to retain the vector notation, one way you can do this is you can do V dot V, that gives you a scalar, and then you can take that velocity again and you can divide by the magnitude of the velocity. This is going to give you a unit vector in the same direction as the relative velocity. So you have the magnitude squared multiplied by the unit vector, and then that is going to yield a vector for the drag force. Now, when we talk about relative velocity, there's all kinds of relative velocities. You could have, if we're talking about bodies, we could have VAB, or we could have VBA. And these are both relative velocities. There's a relationship between them, and it's a negative. One's the negative of the other. So, what is this relative velocity really? It depends. And when I say it depends on how this equation is written. Sometimes you will see this equation with a negative sign on the front, and sometimes you won't. So right now I've written it as positive. So the way that I have written it, this V is going to be the velocity of the flow minus the velocity of your object. So let's say we're looking at this brick right here, and we give this object point A, so this would be the velocity of the flow minus VA. If we put a negative in front, well, if you're doing dot product, then it doesn't matter the order, right? Because this is going to end up squared. But if there's a negative in front, then we just reverse the order of this, and it'll reverse the order of the unit vector. And let's consider really what this means for a moment. Imagine that the flow is not moving. So imagine that velocity of the flow was equal to 0. Then your relative velocity is just going to be negative VA. Dot product is going to yield VA squared. Unit vector is going to be in the same direction as your negative VA. So you can imagine taking that negative and bringing it to the front. And really what we're saying is take the velocity of your object, whatever the velocity is, and reverse the direction, and then that's going to yield your drag force. So that's why we set it up this way. If you reverse this, then you're going to swap the sign. So again, just pay attention to how the equation is written and to how this velocity has been defined. Let's take another case though. Consider, what if you have a stationary object and you have an active flow? So this is this could be a tree in hurricane force wind, and that hurricane force wind is going to generate significant force on the tree, and that's actually a drag force, and that is the force capable of tearing the tree out of the ground. So this would make this a very large number, and VA is 0. So you're going to yield a positive drag force, and it's going to be in the same direction as your hurricane force wind. So if you have, we could do a building now. Here's our building, right? Here's some windows in it, and you have very strong winds coming and blowing on your building. Well, then the force, the drag force resulting, is going to be in the same direction as your flow. And of course, if you have something like an airplane in flight, then clearly the airplane has a velocity, and there's probably a little bit of wind as well. So this can create headwinds, this can create tailwinds, cross currents, etc. So when we do this in dynamics, we want to make sure that this is a vector. All right, so this is a generalized drag equation. This is useful for many macro scale situations. You might have small changes to these equations based off of specific conditions, but how do we build these drag coefficients? I said the drag coefficients are modeling things like laminar versus turbulent flow, and it's also modeling geometric shape. This drag coefficient is actually found through experimentation. You build you take a wind tunnel and you build a little model, and you put your model or maybe even a full-size object in a wind tunnel, and you can, by controlling the wind tunnel, you can control things like the flow rate so that you control the Reynolds number. You can control temperature, which means you're controlling density, right? Because density is a function of temperature. And then you measure the drag force on your object, and then using the equation, you can then calculate what is the drag coefficient for this particular geometric object in this particular flow. And if aspects of the flow change, well, then this drag coefficient is going to change. If the geometric shape changes, then the drag coefficient changes. One thing to keep in mind is hypersonic flow, for example, the air will heat up. So your temperature will affect your density. If you're looking at space shuttles or rockets on re-entry, those things can come in at re-entry at tens of thousands of kilometers an hour. So there's a lot of heat that is generated from the friction. So the friction itself is going to heat up the material and heat up the air around it, and then that is going to affect the local densities, etc. So final comment about this, just be aware that under certain conditions, this equation can become more complicated. So this is a general equation for drag, so it's a good first guess. Okay, let's clean this up and let's move on to the next case, which is Stokes' law. Stokes' law is a specific application of drag, and we're only going to apply it under certain circumstances. So there's a series of assumptions in order to use Stokes' law. First of all, your object needs to be a small spherical object. Next, it needs to be smooth on the surface. Next, the flow is low Reynolds number flow. So this RE is your Reynolds number. So low Reynolds number flow, which means it is laminar. And then also, if you have multiple objects, multiple particles, then the particles do not interact. Now, if you can satisfy these assumptions, so what kind of situations satisfy these assumptions? Well, the small object, we're usually talking about sub-millimeter or so, something in that range. So if you're doing anything with micro objects, if you're doing anything with biological systems, and you want to model things like molecules, particles, cells, things like that moving around in fluids, then Stokes' law is a very nice drag model for those specific situations. And here's the equation for Stokes' law. The drag force is going to equal 6 pi multiplied. I'm going to use the character mu, and I'll tell you what that is in just a moment, and then multiplied by r, and then that is multiplied by v. So 6 is just a number, pi is just a number. Mu is the dynamic viscosity of the fluid. The units of this are kilograms per meter second. Next, your radius of your object. Again, this is applicable for spheres, so the radius of the sphere. Of course, this is going to be meters squared. And then the V is still your relative velocity with respect to the flow. And again, look at how I've written the equation. I've written it with a plus sign in front. You could see this with a negative, and if you see it with the negative, that means the order of the terms in your relative velocity reverse. One thing that's nice about Stokes' law is we don't have to deal with the v squared, so we don't have to worry about generating the unit vector. You literally calculate this number, and then you just multiply that by the relative flow. Okay, so, oh, and units for this one, meter per second. And of course, we can multiply these things together, and we see that we get a kilogram. This meter cancels with that one, so kilogram meter squared per, oh, there we go. Yeah, that's it. Okay, so the meters cancel, we're left with kilogram meter per second squared. Okay. All right, next, let's clean this up and let's talk about just a handful of other considerations. What if you're simulating something like a rocket or a spacecraft? A few things to take note of in the drag equation. Remember, this is 1/2 rho CdA, and I'm just going to write v squared. We know how to deal with that. Consider it with something like a spacecraft. First of all, you're impacting a lot of air on the front of your craft, and that could be affecting temperature. But also, if this is your planet, Earth, and you are launching off of the Earth, and you are leaving the atmosphere of the Earth, then as you travel away from the Earth, then the atmosphere is going to thin. So your density of your fluid is going to diminish with an increase in your elevation. As you get away from the Earth, right, the density of the atmosphere is going to thin. So depending on your simulation, your density could be a function of many things, temperature and elevation. And recall also the drag coefficient. That's a function of not just the geometric shape, but also the flow around the craft itself. So you could have situations where your drag coefficient also is changing. And what if your craft is turning? If your craft is going directly into the fluid, then we know what the impacting cross-sectional area is, right? We know that air is going to be striking the front of the craft. But as your craft begins to turn, consider that the velocity at a certain moment might actually be something like this. You could have a velocity that is not directly in line with the geometry of your craft, which means the air is now going to be striking additional surfaces. So I'm not going to offer complete solutions to all of those cases in this video. It's just an acknowledgement that if you're going to be working these types of real world problems, there's much more that goes into modeling the drag than just this. In addition to modeling the drag, you could also have aerodynamic lift generated from the flow across your craft. So when you're simulating bodies like this, you have to take into consideration the change in linear momentum generated from the ejection of the fuel, the potential well that you're operating in, so gravity effects. There's going to be viscous friction drag that is a function of multiple parameters, and also aerodynamic lift, etc. So these models actually get fairly complicated, but again, this drag model, this is a good place to start. Next, one other comment and or one other system, and we'll call it for the day. What if you're modeling something like a pendulum, and we want to consider what is the friction acting on this pendulum? Well, there's two sources. First is the friction acting on the pendulum itself. This pendulum could be submerged in a fluid. It could be submerged in oil, something like that, inside of a housing or inside of another machine. Think of internal combustion engine. All of your components inside of the engine itself are just swimming in oil, so there could be friction on the object itself from moving through the oil. Next, you could, if your object is rotating, you could also have some kind of friction at this mount. Consider we could have perhaps a system of bearings at this mounting location. And we would therefore need some kind of model for the friction with the bearings. An easy model to implement for something like this is we could say, let's model it as, I'm going to write it as a torque. You could also think of this as a moment due to drag, or a torque due to drag. And let's say that we have some drag coefficient beta, and we'll let this beta represent numerous other parameters. So we have beta, and then if this pendulum is rotating with an angular velocity theta dot. Well, if theta dot is positive, that means the drag torque at the joint is going to be in the opposite direction, because the friction is always going to oppose the motion. So let's say that we have theta dot, and maybe we raise this theta dot to some value. For example, it could be something similar to velocity squared. And if we square it, then we lose the vector, which means we need to do theta dot divided by the magnitude of theta dot. This would give us the unit vector. And right now, the way I've written it, we need a negative on the front. So here's just another example of a type of friction equation you could use. Now, this whole study of things like friction and bearings, this actually has a whole class of study. This is called tribology. So if you are interested in how to accurately model things like friction and bearings, this is the field of study for you. Okay, so what should you take away from today's video? There's a lot of ways to model viscous friction. It depends very much on your situation, the shape of your object and the fluid that you're moving through, and what exactly is the nature of the mechanism itself. I've given you a few equations that you can use as starting points to give you general ideas about what you can expect, but oftentimes many of these parameters, so the CD, perhaps the beta in this case, these parameters are actually generated through experimental testing. So when you go and you purchase things like bearings, because you can just go online and purchase bearings, and the manufacturers will give you estimates of the friction associated with those bearings. Oftentimes they are generated from empirical data. Okay, so that's it for this video. Best of luck, everyone. I'll see you next time.